Today, we are officially stepping into the big leagues. We're tackling Chapter 05 of our design journey, utility scale design. Think of this as the ultimate test, the true examiner of your engineering skills. Up until now, we've covered individual components and foundational math. But today, we combine absolutely everything into one final, massive challenge.
I really need you to understand that this is a serial chain of learning. You literally cannot skip ahead. Every single component you learn to size in Chapter 4 comes into play right here. If your sizing is off, you don't just trip a local breaker, the entire regional grid feels the impact. This is where all that training seamlessly connects to a real-world, high-stakes application.
Here is our roadmap for today. We're going to cover the paradigm shift in utility design, how we protect the grid, and then we'll tackle two massive case studies before finally compiling the engineering deliverable list.
Okay, let's dive into this. Section 1. The paradigm shift, moving from available space to grid impact.
To succeed at this level, you've got to fundamentally change your mindset. In C&I, or commercial and industrial scale, your workflow usually starts with the available space and figuring out what percentage of the client's bill you can cover, right? But utility scale is a whole different beast. It all starts with the client requirements and, crucially, the grid impact study. Your main concern isn't just generating power, it's defining exactly how much power the grid line can withstand without going down.
Moving right along to Section 2, protecting the grid and mastering that grid impact study. The core engineering challenge here is calculating the precise power on each bus and ensuring strict compliance with voltage ranges. That's where your primary defense mechanism comes in, QV, or reactive power compensation. When you inject massive amounts of power, you risk severe voltage drops. QV compensation is how you supply or absorb reactive power to stabilize those drops, keeping your power factor exactly where it needs to be at the point of common coupling.
If you fail to mitigate these effects, you trigger some really dangerous grid disturbances. We're talking voltage swells, sudden voltage dips, and nasty harmonic distortions. In fact, you have to keep your total harmonic distortion strictly below 3%. Mitigating these specific effects is basically the entire focus of your grid impact study.
All right, Section 3 brings us to our first real-world boss fight. Case Study 1, the 60-megawatt peak giant.
168. I want that number to just sink in for a second. That is the quantity of massive 330 kVA string inverters required for this grid-connected plant. Coordinating the DC inputs and AC outputs for 168 of these units requires an entirely different caliber of engineering.
And this brilliantly illustrates the sheer physical scale we're dealing with. To manage the power from all those inverters, this 60-megawatt plant needs 6 separate transformer stations, each rated at 9 MVA. From there, it all feeds into a heavy-duty medium-voltage switchgear featuring 12 individual cubicles. That switchgear collects all this generated power and safely exports it right to the grid.
Let's shift gears to Section 4. Case Study 2. The 20-megawatt-hour utility scale BESS.
So what happens when you need to actively stabilize grid voltage? You integrate a battery energy storage system, and the scale here is just incredible. We are looking at a 20-megawatt-hour project using 4 5-megawatt BESS units. It's paired with a 5.2 megawatt peak solar plant, that's 4.8 megawatts AC. To run this whole setup, we're utilizing 16 grid-connected 330 kVA inverters alongside 24 power converter systems, or PCS, each rated at 213 kW.
Let's move to and see how this builds from a high-level sizing spec into the incredibly harsh reality of an actual single-line diagram. Look at the complex electrical interlocks required here. You have to safely coordinate the solar generation, the grid connection, and the bidirectional power flow of the battery units without a single fault.
Finally, Section 5, the engineering deliverable list, forging your final weapon. So, you've done the math and stabilized the grid. How do you actually hand this over to the client? You build the EDL, organized into 5 distinct categories. First, layouts, covering PV, equipment, and civil works. Second, the SLDs, detailing power, protection, metering, auxiliary circuits, UPS, monitoring, and SCADA architecture. Third, your design reports, including your design basis, codes, and calculation and simulation reports. Fourth, the technical data sheets for every component used. And finally, the material list, or BOM, for the PV plant.
So the crucial point is that these 5 pillars constitute the official base design package. This is what proves your work is ready for client approval and, ultimately, construction.
Before we wrap up, I want to leave you with this critical piece of design philosophy. Standard test conditions are great for a lab, but they will fail you in the real world. You must absolutely always design for worst-case temperature extremes to avoid inverter overvoltage and guarantee realistic energy yields.